All right, so I'm going to lecture on section 2.1, and because it's kind of the first lecture of the semester, I should probably just say some generic things about the course, just so you get an idea of what's going to be coming up and what you should be doing as you go through these videos. So if you haven't already, you should get to my webpage, and if you log into Canvas, there's got to be a link somewheres to my webpage in Canvas, and I can show you what the web address is if you want. You don't need to get to my webpage through Canvas. So the copy of the syllabus for this semester, but it's gonna, my web address shouldn't change. So this address right there, if you just type that in, that will take you straight to my web page. You don't need to use Canvas to get to my web page, but you can get to my web page through Canvas. Also, if you searched me on YouTube, you can find a link to my web page, and I should probably show you that. I'm just getting used to using YouTube, so my YouTube page is, as kind of crappy as my web page is too. But I'll show you in a second that you can also access my web page from YouTube. So real quickly, maybe I should turn my computer on so you can see my web page and what my YouTube page looks like right now. So if you typed in my web address or the URL for my web address, this is what you'll get to, something that looks like this. Everything that you're going to need for this course is going to be scrolled down a little bit and in green. If you look at my web page when it comes up on this particular monitor, it says scroll. I see scroll down for Math 142 and Math 151 links. Because this is Math 151, you're going to want to scroll down to that section of my web page. Basically everything you need for the course is linked to from this web page. I don't have a book, but I've written problems to kind of work as a book. So if you get to my web page, scroll down to the green links for Math 151. The copy of the syllabus for the semester that you're enrolled will be there, along with every single problem, answer, and worked out solutions to the problems. And if you come to class, the first day of class, I'll talk in more detail about what's on my web page, but you can explore it for yourself for now. If you go to YouTube, and then just search for me, and then somewhere on the first page of links, you'll see a stunning picture of me and at least a link to my web page. If you haven't seen me before, then you'll see me for the first time. That's my YouTube page. And then right on the top of my YouTube page, there's a link that says my web page. That'll take you back to my syllabus. Every single video that you're going to be watching this semester, you can get directly from YouTube. So if my web page is down, because sometimes the campus server goes up and down, you can just navigate to YouTube and you can find all the videos that I have. I believe if you just clicked on the videos link, you'll see gobs of videos. And then if you click on the videos and then you click on playlists, then the videos are organized by chapter. You'll have to scroll down to find the 151 videos. And as I scroll down, I eventually find the 151, which I just called College Algebra, because that's the name of the course, and I thought that was a better way to do it. And you can follow the link under the picture into the chapter, then you can navigate to the video. If you click on a picture, it starts like with the first video. It doesn't give you the option of selecting a specific chapter. So let's say I wanted to go to my chapter 8 in college algebra. If I clicked on that, it says play all. It's going to play every video, which is a bit ridiculous. If you click on the blue link, then it's going to take you to a page that has all of the videos for the chapter. So, and you can just select the one that you want to select. And there's a little time signature so you get an idea of how long the video is before you commit to sit down and watching it. Because this is our first video, you don't really have a big clue for how I lecture unless you have already taken me for a class, and then you'll have a better idea of how I lecture. But for the most part, when I do a lecture or when I do a video, I solve essentially every even problem in a section. So in a bit today, when I start section 2.1, I'm going to print out every single even problem from section 2.1 that's available on my webpage. It would be wise if you at least went to my webpage and opened up the problems. If you're ambitious, while you're watching the video, as I do an even problem, you might want to do the corresponding odd problem. In a second here, I'm going to do problem 2 in section 2.1. After I do problem 2 in section 2.1, you should be able to do problem 1. And then I'll do section 2.1 number 4. After I do number 4, you should be do number 3. Ultimately, I want you to do all the odd problems in every section. Every now and then, as I'm going through a video, I'll say, don't worry about doing this problem. This is just something that is in the video that I'm supposed to cover, but I know I'm never going to test on it, and it's not that important, so you can not worry about it. But you should, at some point, for every time I do an even problem, you should do the odd problem that kind of pairs up with it. And that'll give you a good gauge of where you're at. So before today's lecture, I should probably click on the link on my webpage that says Chapter 2 Problems. And under that link, you'll see everything that I'm going to do in class and then everything you're going to do. If you follow the link that says Chapter 2 Answers, for every odd problem that you're supposed to do for homework, it's going to have an answer without work. And if you click on the link that says Chapter 2 Solutions, it's going to have a worked out solution or an explanation of how I got my answers. So at a minimum right now, you should have found my webpage, maybe click on the link that says Chapter 2 Problems. Everything is a PDF file, so hopefully you don't have any issues with opening my files. You don't have to print these out if you don't want to, because they get kind of long, but you certainly can print them out if it helps you to have them in front of you as you go through the videos. It takes an insane amount of time on campus to open up a PDF file, and it's not really that terribly long, but there it is. And you'll see that this is, I think it was like 18 pages, but this is what I'm going to be doing when I do my lecture. I'm going to lecture in section 2.1 today, and there are even and odd problems. I'm just going to do every single even problem with the hopes that you can do the odd problems after I do the even problems. Today and a lot of days during the semester, I'm going to do some calculator work, and specifically, you need a calculator that does graphing. If you had me for intermediate algebra, I don't use a graphing calculator for that class, and I kind of like the intermediate algebra calculator better than this calculator, but that intermediate algebra calculator that I use doesn't do graphs, and you won't be able to get through this course very nicely without a graphing calculator. And the only graphing calculators that I know how to use are the Texas Instruments Model 83 and 84. Those I can work pretty well and do everything I need to do for the course. Quite honestly, I've seen some Casio calculators that have much better screens that are actually superior to the TI-83 and TI-84. It's just that I don't know how to use them. So if you have one, it's probably a better calculator, but you're kind of on your own. You can come into my office and I can try to help you do the things we're going to do. But if you want to be safe, as I go through the videos, I will, when I need a calculator, use either the TI-83 or TI-84. They work identical to each other. The 83 and the 84 are more or less interchangeable for our class. The keystrokes on the 83 will be the same as the keystrokes on the 84. So you should always have one of those handy just in case we get to a section where we need a graphing calculator. And in this section, you probably could get by without a graphing calculator, but it'll make it a little bit easier. When we come to a test, you're welcome to use your graphing calculator, so you might as well get comfortable using it. It'll definitely give you a little bit of an advantage. If you come to class the first day, or shoot me an email or come visit me at my office, I can tell you more specifically how the course is going to work. That takes about a half hour or so, and I didn't want to do a half-hour lecture on top of lecturing how the course works. So I'm going to get started doing section 2.1, and somewhere on your syllabus there's going to be a calendar that tells kind of you what you should be doing by when. And for this particular semester, it's a spring semester. It kind of gives me an idea that by class on January the 22nd, which could be January whatever, or September or whatever, or August whatever for your semester, it kind of tells you I should have watched all the videos by a certain date. And anytime I watch a video, it's implied that while I'm watching the video or after I'm watching the video, I should be doing the odd homework problems. So this is just a printout of all the even problems, and I tried to make them a little bit bigger so that it shows up pretty decently, and then I'm old, so my eyes don't work so well either. So I think I'll get started. And these videos get insanely long because apparently I don't know how to control what I don't say, and I try to say everything I think that you might have a question over, and that makes them get real lengthy. As you're watching a video, if you just in a section of problems, if you know how to do it, you're most welcome to fast forward. You don't need to watch me do every single even problem. But for that matter, some students might need to see me do a problem 2 or 3 times before they get it sunk in what I actually want you to do. I'm always available in my office for a bunch of hours every day. So if you're stuck on something, visiting me in my office is probably the best idea. Shooting me an email is semi-effective, but sometimes it's hard to answer math questions via email. It's just hard to do. So I have gobs of time to help you out if you come visit me in my office. All right, I was just making sure the video thing was working. It would have really not been fun had it not been working. So this course has a lot of overlap between it and intermediate algebra. And if you haven't forgot intermediate algebra, then there's going to be a ton of things that are easy for you. But if you've forgotten intermediate algebra, then you'll have to relearn this on the fly. So the first few problems in section 2.1 ask me to find x-intercepts and y-intercepts, and they don't give me an equation, it's just a graph is given. And very specifically, if I find a point where the graph touches or crosses the x-axis, that point is going to be an x-intercept. And if I find a point where the graph touches or crosses the y-axis, that point's going to be a y-axis, a y-intercept. So as I look at this graph, and I look across the x-axis, the 2 points that I circled are going to be x-intercepts because those are points physically on the x-axis. And it's best if you're asked to find an intercept, because an intercept is a point and a point has an x and a y, to write your intercepts as points. That's actually the point 2, 0. And the second one that I circled is the point -2, 0. If this was a test, I wouldn't want it, but I would live with you writing x equal to 2 and -2. I'd understand that that would be the a reasonable answer for the x-intercept, but it would be wrong, and you would lose points if you just wrote -2 and 2 or 2 and -2, because I couldn't tell whether the 2 and the -2 you meant them to be x-intercepts or y-intercepts. So this would be best. This I wouldn't lose credit for, and that you'd definitely probably lose points. I give partial credit if you make a mistake that's not a horrible mistake. And I'm not sure what I would do if you did that. So you're going to want to write your answers in nice forms. So the y-intercept is that point there, and that is the point 0, 4. And again, it would be okay if you just wrote y equal to 4. If you take calculus after this class, you might get a teacher that doesn't like that. Very specifically, the day calculus teacher at GCC North right now would take points off for certain if you wrote just y equal to 4. And same deal, if on a test for me, if I asked you to find the y-intercept and you just wrote the number 4 and didn't indicate that's a y as opposed to an x, you're going to lose points. So no algebra for that problem, so it went pretty quickly. No algebra for problem 4. It's in the same grouping of problems, so instructions say find the x and the y-intercepts, and I'm going to do the same thing. I'm going to look at the x-axis, and any place where the graph has a point on the x-axis, those are going to be x-intercepts. So it has 3 x-intercepts. And my x-intercepts are going to be that point. Nicest way to write that's the point -3, 0. This point, best way to write that's -1, 0. And that point, best way to write that's 2, 0. And again, I live with writing x equal -3, -1, and +2, but I prefer it written as a point. And then for the same problem, if I wanted to do the y-intercept, I just need to find the point on the y-axis. And for these problems, all the intercepts are going to be integers. It might, it might not be completely convincing that this is going through exactly at the point -1, 0, but it's supposed to be. And the y-intercept, I would write that as a point 0, -6, because points on the y-axis are all 0, then some number. And again, same deal. If you wrote y equal to -6, I would live with that. But if you just wrote the numbers -3, -1, 2, or -6 without an x or a y, or without writing them as a point, you lose points. So that should inspire you to be able to do problems 1 and 3, because problems 1 through 4 all have the same instructions. The even problems should pair up real nicely with the odd problems. So if you have the problems open, take a second, if you have the time, do problems 1 and 3. You'll be happy that you have those out of the way. The next group of problems, same instructions, find the x and the y-intercepts. Not so nice because I don't have a picture. And if I don't have a picture, that means I have to do algebra. It's not terribly hard algebra until we get into factoring problems. So for each of the problems between 5 and 18, when I'm asked to find an x-intercept, I'm going to replace the y with 0 and solve for x. And then when I'm asked to find the y-intercept, I'm going to replace the x with 0 and solve for y. So you're going to have to get used to my writing. I apologize, it kind of bites. Hopefully I speak clear enough that if I wrote something that you can't read, that at least you can hear. Usually anytime I write something, I say what I write. The idea being my writing kind of sucks, and if you can at least hear it, you can figure out, well, what the heck that actually meant. Like, that's supposed to be an and symbol. But algebraically for this problem, the first thing I'm going to do is find the x-intercept. I could do this in my head. When we get to the tests, if you do algebra in your head and you make a mistake, I can't give you any partial credit. If you do algebra and show me the work and you make a mistake, then I've got some flexibility in giving you partial credit. So it's always safer to show work. And I show more work than I think you need to show, but it's never a bad idea to show more work than not. So for this problem, when I plugged 0 in for y and simplified the left-hand side, I got 2x on the left side, 12 on the right side. There's no exponent, so I don't have to worry about factoring. If I stopped and said x equal to 6 for the x-intercept, that would be fine. I would guess when you get to the test question that asks you to do this, that there's going to be a spot where you're asked to write the x-intercept and a spot where you're asked to write the y-intercept. But if there wasn't, on an answer blank, if I wrote 6, 0, that would be completely fine. I can understand that that is an x-intercept because it's a point on the x-axis. To find the y-intercept, I replace the x with 0, so I go 2 times 0 plus 4y equals to 12. The 2 times 0 becomes 0, so you get 0 plus 4y equals to 12. 0 plus 4y is just 4y, so this reduces to 4y equals to 12. And then divide by 4, and gives me y equal to 3. And in for my answer, it would be best to write that as a point. I plugged in 0 for x and got 3 for y, so that would represent the point 0, 3. Whereas the top one, I plugged in 0 for y and got 6 for x. And similarly to the non-algebra problems, if for the x-intercept you wrote x equal to 6, and for the y-intercept if you wrote y equal to 3, I'd live with that. Those, again, aren't the ultimate best answers, but I can live with them. So that should motivate you to do problem 5. Problem 5 should have the same skill set as problem 6. So if you have the time, do problem 5 now while you have something in your mind that is probably useful. 8's quite a bit harder. Immediately when I see the squares, I assume I'm either going to have to factor or solve with square roots to get the intercepts. And in this problem, I think I'm going to have to solve with square roots. So the first one I'm going to find is the x-intercept. And anytime I'm not given a graph and I have an equation with both an x and a y, to find an x-intercept, you let y equal to 0 and solve for x. So I'm going to go 0 squared equals x squared minus 25. 0 squared is 0. That would give me 0 equals x squared minus 25. And one hard thing about college algebra is you're supposed to remember a lot from intermediate algebra that you might not remember. I'm going to solve this 2 ways, but you only need to solve it 1 way. So this can be solved by factoring, or it could be solved by taking square roots. And if I solve it using square roots, you can't forget you need the plus or minus. So solving for the x-intercept by factoring, I'd go x squared minus 25 equals to 0. Solving by factoring implies I know how to factor that. This is a difference of squares. There's 2 terms with a minus between them. The exponent is even. The number has a nice square root. Hopefully that's kind factoring for you. And you could factor that quickly into x plus and x minus 5. And if you're solving something by factoring, it has to be equal to 0. Once you get the problem both factored and set equal to 0, then you take the inside of each parentheses and set them equal to 0. And again, this is usually the kind of stuff I would do in my head. But if you want to be safe on the test, the more work you show, the more partial credit I can give you if you make a mistake. If you can go from this parentheses to the x-intercepts without showing this algebra, setting the parentheses equal to 0, minusing 5, and adding 5, that's completely fine. So this tells me that the x-intercepts, there's two of them, and I'm going to write the intercepts as points. I plugged in 0 for y and got -5 for x and +5 for x. So that would represent the point -5, 0 and +5, 0. I'm done finding the x-intercept, but quite honestly, that's not probably the way I would have found them, even though it was easy factoring. The other way I could have found the x-intercept is with square roots. And that's probably the better way here. At least it's something you need to remember, solving with square roots. Solving with square roots only works when there's one letter. It doesn't work when there's two letters. So if this was like x squared plus 5x minus 25, if there were two letters, I couldn't solve with square roots without completing the square, and that I don't want to do. So to solve with square roots, unlike solving by factoring, you need to isolate the term with the square, get the number on one side, the letter that's squared on the other side, and then square root plus or minus square root. If you don't do the plus or minus, you're only going to get one of the two x-intercepts and not both. On the left-hand side, I will put the square root and the plus or minus to make sure I get both the positive and the -5. And on the right-hand side, square rooting cancels out the exponent of 2. So I get x is plus or minus 5. That's just another way of saying x equal -5 and x equal to 5. And so that's the x-intercept part. That's actually the less tricky part. The harder part is the y-intercept, because it's some sense a trick. So I'm going to let x equal to 0. I'm going to go y squared equals to 0 squared minus 25. I'm going to get y squared equals to minus 25. And again, I could attempt to solve this two ways. I can solve it by factoring. To solve it by factoring, I need to add 25 to both sides and make it equal to 0. Turns out that if I did that, if I added 25 to both sides and made it equal to 0, I'd get y squared plus 25 equals to 0. And this is prime. It doesn't factor. This is a sum of squares, and sums of squares are prime. So that wouldn't have been, the factoring way wouldn't have helped me anyways. So I'm going to do the square root way. I'm going to go square root plus or minus square root. And on the left side, square rooting cancels out the square, leaves me with the y. On the right side, the plus or minus symbol doesn't go away, but I'm going to get something with an I. To get that square root done on my calculator, let me get my calculator put into a nice mode. I'm going to hit the mode button, and I'm going to go down. So the mode button's right next to the second button. And I'm going to go down to where it says real a plus bi, and then get the a plus bi flashing and hit enter. That should be fine for the whole semester. So now if you hit your mode button, if you had the a plus bi darked out, it'll give you imaginary numbers, and this is going to be an imaginary number. So I've set my calculator up kind of, at least for now, for the semester. I'm going to hit the second button in the mode again and do the square root of -25. I can't do plus or minus, so I do the second button in the x squared key, the negative in the very bottom row of the calculator, and I type the number 25, and I get 5i. Because the square root of a negative number is an imaginary number, you get an I when you simplify that square root. It would probably not be best to say that the y-intercept is the point 0, -5i, and 0, +5i, because those aren't points that I see. Those are imaginary points. And when you get an I when you're trying to find an intercept, the graph doesn't cross that axis. It's a little bit tricky. So let me show you pictorially why the x-intercepts are -5 and +5, 0, and the y-intercepts aren't any. So if you're trying to find an intercept and you get an I, that means it doesn't have that intercept. Another way to do this problem would have been to actually solve it graphically. And if I graph this equation on my calculator, I can show you the intercepts of 5 and -5 for the x, and to show you that they don't have y-intercepts. Unfortunately, my calculator doesn't let me have an equation solved for y squared. So on my calculator, if I want to graph this, I need to do a lot of extra work. So I'm going to square root it. Square rooting cancels out the square and gives me a y. And then on the right side, I get plus or minus the square root of x squared minus 25. I can't enter a plus or minus on my calculator, so when I graph this, I'm going to go y1 equals the square root of x squared minus 25, and y2 equals the negative square root of x squared minus 25. I actually have to enter this as two separate functions to get it entered. This doesn't reduce. You can't make this x minus 5. You can't take square roots of terms individually when there's a minus sign between them. So I'm going to break my calculator out now, and best I can, I hit my y equals button, and I already graphed something, probably as writing a test, so you can write that down as probably on a test at some point. I'm going to clear this out, hitting the clear button. Then I'm going to go second and x squared for the square root. The x is right under the mode key, so I'm going to go x and then hit the x squared key to get the exponent of 2, and then minus 25. Close out the parentheses. My calculator gave me a left parentheses. I'm going to give it the right parentheses. This plus right there is supposed to be a minus, and it's supposed to be the minus right under the times key. There's two minuses on our calculator, the minus in the bottom row and the minus that's a subtraction. This is for it's a subtraction. So now I'm going to hit enter. And for the next one, I need the minus square root of x squared minus 25. This is when I need the minus in the bottom row of the calculator. It'll look a little bit smaller. And then second square root x squared minus 25. So I use both the minuses here. This is for a negative, and this is for a minus. Negative in the bottom row of the calculator in the parentheses, the negative in the minus. I don't know what window I had when I graphed previously. So to get my calculator's window kind of into a decent window, I'm going to hit the zoom button, which is in the middle of the top row. Arrow down to number 6 that says standard, and then it's going to graph each equation one at a time, and that's going to be the graph that I'm looking for. And it doesn't do a stellar job, but you can kind of see the graph looks something like this. It's supposed to look more like that. My calculator has some flaws in terms of it doesn't do algebra per se. It does something that simulates algebra. That's the picture that we're supposed to get. It looks like it has a little gap there, but it's not supposed to, but it's the best I can do with this particular technology. So this right here is the point -5, 0. This right here is the point +5, 0. Those are the x-intercepts. And if I look at the y-axis on the graph, you notice the graph doesn't cross the y-axis. That's why it's appropriate to say the graph has no y-intercepts. Because when I do graphs, I don't plot the i's. I only plot points that are real points, and it doesn't plot the imaginary point. So the best answer for this last problem is that it doesn't have a y-intercept because the graph doesn't cross the y-axis and has two x-intercepts, -5 and +5. You need to do the algebra on the test as opposed to just graph it on your calculator. 10's not fun because it has bottoms-up factoring. The x-intercept part of it's the bottoms-up factoring. If you're not familiar with bottoms-up factoring, that makes no difference to me. You need to be able to factor something like this, where there's a number in front of the problem, number in front of the x squared. If you don't remember how to factor this, you can go to my intermediate algebra section 1.3 videos, and it'll teach the method I'm going to show right now. If you know how to factor this, just factor it and don't watch my factoring. But if you don't know how to factor this, I'm going to use bottoms-up factoring. And I'll do the bottoms-up factoring off to the side here. So this is a method for factoring when you have 3 terms and a number in front of the x squared. There's multiple steps. The first step is to multiply. And students generally do that step fine. They forget the last step. So the multiply part is I'm going to multiply the first number and the last number. That's 2 times negative 9. I get negative 18. So I'm going to write this as x squared plus 3x minus 18. This is bottoms up factoring. This is a way to factor that 2x squared plus 3x minus 9. That works. But if you don't use bottoms up factoring, I don't use it, you can get it factored just as fine using another method. So after the first step in bottoms up factoring is to multiply the outside numbers and put the result into the last number. The second is to factor this. Hopefully you can factor this. If you can't, that's section 1.2 in my intermediate algebra. This factors into x plus 6 times x minus 3, because the last have to multiply to negative 18 and add to 3 essentially. And then if you don't do this part, divide, reduce, and bottoms up, then what you write won't be factored properly. So I started off multiplying that negative 9, which was the last number, by 2. I'm going to get that 2 divided back out. That's the divide part. Now reduce. 6 over 2 reduces to 3. I'm going to write an x plus 3. Second fraction doesn't reduce. It needs the bottoms up part, the bottom being the denominator, and bringing it up in front of the x. If you've never seen that before, one example isn't near enough for teaching bottoms up factoring. But if you've never seen it before, hopefully you didn't forget how to factor something like this, and you factored it without using that method. One way or another, you need to get this factored. You could technically solve this by the quadratic formula, but we're going to need to factor enough this semester that you should remember how to factor. So now that I have the left side 0 and the right side factored, what I should do is set each parentheses equal to 0. The x plus 3, you just minus 3 from both sides. That will take me to one of the x-intercepts, which is going to be negative 3. And the 2x minus 3, I add 3, which gives me 2x equal to 3, and divide by 2. And I get x equal to 3 halves. I prefer fractions over decimals. Prefer improper fractions as opposed to mixed fractions. If you wrote 1.5 or 1.5, I'd live with that, but I prefer what I have written there. So now I'm going to write down the x-intercept part of the answer. There's going to be 2 of them again. If I graphed this graph would cross the x-axis at the point negative 3, 0, and at the point 1.5, which is 3 halves 0. That's the harder part. The y-intercept is the easier part. The y-intercept, I just plug in 0 for x. So I would go y equals 2 times 0 squared plus 3 times 0 minus 9. Orders of operations want me to do exponents first. 0 squared is 0 times 0, which is 0. And again, you don't need to show as much work as I'm showing. I'm just trying to show all the steps just in case you need to see them. So I did exponents, and then I multiplied 2 times 0 and 3 times 0, and then 0 plus 0 minus 9 is minus 9. So this graph has both an x and a y-intercept. And the y-intercept's the point 0, negative 9. So this would be the ultimate that you could do if this happened to be a test question. I've showed every bit of work I needed to show. I showed even how to factor that. If you can factor this in your head, or if you factor it by grouping, that's completely fine. Because it's a quadratic equation, you could use a quadratic formula. So if you remember the quadratic formula and you solved this by the quadratic formula, got the same answers, that's beautiful too. Notice my answers, I wrote the intercepts in nice forms. I'll keep going here. 12 didn't, for whatever reason, blow up very nicely. This is problem 12. So first thing, x-intercept. And it doesn't matter if you find the y-intercept first and the x-intercept second. But you'll notice I'm keeping my work easy-ish to follow. It's going to make it, when I'm grading, beneficial to you. If you make a mistake and it's easy for me to figure out your mistake, it's going to be easier for me to give you partial credit. If I can't read your work or tell what you've done wrong, then it's going to be hard for me to give you the partial credit. Just like in the last problem, do my orders of operations. To find an x-intercept, you plug in 0 for y. I do the exponent first. 0 squared is 0. And then this gives me 0 plus 0 plus 9. And that's x equal to 9. So in for my answer, my x-intercept is going to be the point 0, 9. And the y-intercept, I'm going to have to do factoring. To do the y-intercept, I plug in 0 for x. I get 0 equals to 2y squared plus 9y plus 9. Bottoms up factoring again. Again, you don't have to be able to do bottoms up factoring. You just need to be able to factor this. And usually, if I can, I do my bottoms up factoring on the side. The reason I'm using the bottoms up is because of that 2 in front of the y squared. And for bottoms up factoring, the first step is to multiply. So I multiply the first and the last number, that 2 and the 9, and I multiply to be 18. I take the 2 away from the y squared and incorporate it into the last. So that's the multiply part. And then the next part is factor. And that's easy-ish factoring. That's just y plus 3, y plus 6. If you can't factor that, then you need to watch my section 1.2 intermediate algebra. And then divide, reduce, and bottoms up. Started off multiplying by 2. I'm going to divide by 2. First parentheses doesn't reduce, so I bottoms up, bring the 2 in front of the y. Second parentheses, 6 over 2 reduces to 3. So this whole thing factors, and it factors into 2y plus 3 and y plus 3. And you could have the factors y plus 3 first and 2y plus 3 second. It doesn't matter. But that's the only way that it factors. Now that I have it both set equal to 0 and factored, I set each parenthesis equal to 0. The 2y plus 3, I'm going to minus 3 and divide by 2. When I minus 3 from each side, I get 2y equal to minus 3. When I divide by 2, I get y equal to minus 3 halves. And for the y plus 3, you just minus 3 from both sides and get y equal to minus 3. And in my answer, there's going to be 2 y-intercepts. I'm going to write them as points. I'm going to write the point 0, negative 3 halves, and 0, negative 3. Again, if you wrote y equal negative 3 halves and negative 3, I could live with that. But this is definitely the preferred way to write the answer. So hopefully you're keeping up and your algebra skills haven't deteriorated, to the point where they're ridiculous. If they are kind of ridiculous right now, you definitely have time to redeem yourself. But we'll factor a reasonable amount this semester. Probably won't factor as much in here as you did in intermediate algebra. But if your factoring skills are just horrendous, then you should relearn how to factor. Visit me in my office. I might be able to teach you how to factor pretty quickly. Watching kind of the sections 1, 2, and 1, 3 videos for my intermediate algebra would probably not be a bad idea either. So 14 wants me to find intercepts for a fraction. It turns out that to find the x-intercept, it's going to be sufficient just to set the numerator equal to 0. But I'll pretend I didn't know that. So finding the intercepts involve plugging in zeros. The first intercept I'm going to find is the x-intercept. And to do that, I let y equal to 0. So this gives me 0 equals to 2x plus 10 over x minus 5. Turns out that it's enough just to set the numerator equal to 0. So it would be enough or sufficient. If you're asked to solve a fraction equal to 0, it's enough just to set the numerator equal to 0. If you didn't know that was enough, you can solve this by cross-multiplying. In order to solve it by cross-multiplying, I need both sides to be a fraction. To make the left side a fraction, I need to write it over 1. So now I've set something up that I can cross-multiply. Cross-multiplying up, I get 1 times 2x plus 10. Cross-multiplying down, I get 0 times x minus 5. On the left side, 1 times anything is itself, so you get 2x plus 10. On the right side, 0 times anything is 0. So that's why I said it would be sufficient just to set the numerator equal to 0. So anytime I'm asked to find an intercept and it involves setting a fraction equal to 0, it's enough just to set the numerator equal to 0 rather than going through the clearing the fraction by cross-multiplying or some other strategy. There's no factoring here because there's no exponents, so I need to get the numbers on one side, the letters on the other, and then I'm going to divide. And there's only going to be one x-intercept. It's going to be the point -5, 0. So when I go to write my answer, I'm going to say the x-intercept is the point -5, 0. And now I'm going to tackle the y-intercept, which should be easier. To do the y-intercept, I go y equals to 2 times 0 plus 10 over 0 minus 5. You notice in the denominator I didn't use a parentheses. I could have put that 0 in a parentheses, but it really wasn't necessary. So this is going to give me y equals to 0 plus 10 over 0 minus 5. I'm kind of running low on my page here, so I'm going to work to the right. The numerator is 10. The denominator is -5, because 0 plus 10 is 10. 0 minus 5 is -5. And that fraction, 10 divided by 5 is 2, but since it's a positive divided by negative, I get a negative. And then for my y-intercept, I plugged in 0 for x and got -2 for y. All right, getting close to the end of this first style of problem. 16 is another lovely fraction. The y-intercept is going to be easy again. The x-intercept isn't going to be so easy. So I'm going to do the x-intercept first. To do an x-intercept, you let y equal to 0. So I go y equals to 2x squared plus 5x plus 2 over x minus 3. It would have been enough if I just set 2x squared plus 5x plus 2 equal to 0. If I didn't know that, I can set this up to cross-multiply by writing the 0 over 1, cross-multiply up, cross-multiply down. Cross-multiplying up, you get 1 times 2x squared plus 5x plus 2. The other direction of cross-multiplying, you get 0 times x minus 3. That gives me 2x squared plus 5x plus 2 on the left side, because 1 times anything is itself. On the right side, I get 0. Third time, I need to do bottoms-up factoring. I just wanted to, this is probably more bottoms-up factoring than we'll generally get, but I just wanted to make sure you get used to it again in case you forgot it. So the first step in bottoms-up factoring is to multiply. Multiply the outside numbers here. Gives me x squared plus 5x plus 4. Then I factor, and that's reasonably easy factoring. That's x plus 4 and x plus 1, or x plus 1, x plus 4. And then divide, reduce, and bottoms up. I started off multiplying by 2. I'm going to divide by 2. First fraction, 4 over 2, reduces to 2, so I get x plus 2. Second fraction doesn't reduce, so I bottoms up and get a 2x plus 1. So I can rewrite this as x plus 2 times 2x plus 1 equals to 0. And then I'm going to go x plus 2 equal to 0 to x plus 1 equal to 0. For the x plus 2, I minus 2 from both sides and get my first x-intercept at x equal -2. For the x plus 2x plus 1, I minus 1 and get 2x equal to -1, and then divide both sides by 2 and get x equal to -1/2. Too many negatives there. So for an answer here, my x-intercepts are going to be the point -2, 0, and -1/2, 0. Again, that's the best way to write the answer, so I'll just write them the best way. The y-intercept turns out not to be near as hard. It looks like it should be, but it's not. For the y-intercept, I'm going to go y equals to 2 times 0 squared plus 5 times 0 plus 2 over 0 minus 3, just changing the x's to zeros. And then this piece right here is just going to be 2 times 0, because 0 squared is 0. So this is going to be, in the numerator, 0 plus 0 plus 2 over 0 minus 3. That gives me a 2 in the numerator and a -3 in the denominator. That's a correct number for the y-intercept. When you have a fraction that's just an integer over an integer, the negative is flexible, and I would probably either move that negative up to the numerator or write it in front of the fraction. But for this number, you could write -2 over 3, you could write 2 over -3, or you could write a negative in front of the fraction with a 2/3. I would generally, for that 2/3, write the negative in the numerator, but you need to have a negative in the fraction next to the fraction 2/3, or a negative somewhere is incorporated into that fraction in your answer. 18, last problem here. I'll probably solve both these with square roots. So hopefully you can do all the problems, the algebra problems that ask me to find the intercepts. But if you can't, come visit me and I'll try to make it better. So for the x-intercepts, I'm going to plug in 0 for y. So I'm going to go x squared plus 0 squared equals to 25. Notice I didn't use a parentheses there. I probably should have, but it really isn't necessary. 0 squared is 0, so the left side reduces to x squared plus 0 equals to 25. And when you only have one x with an exponent, square rooting plus or minus square rooting is probably the nicest way to solve. So on the left side, the square root symbol gets canceled out. I'm left with an x. On the right side, the plus or minus sign doesn't go away, but the square root goes away. And I'm going to get two x-intercepts, +5 and -5, and I'm going to write them as a point, throwing some zeros in there. So for my x-intercepts, I'm going to get the point -5, 0 and +5, 0. And then for the y-intercept, I'm going to go 0 squared plus y squared equals to 25, which is going to give me y squared equals to 25. I'm going to get the same answers. I'm going to go square root plus or minus square root. On the left side, the square rooting cancels out the square. On the right side, the square root of 25 is 5. And for my answer, for my y-intercepts, there's going to be essentially the same intercepts, except I get a 0 first and the number second. So that's the first style, or the first concept in this section. The big difference in terms of difficulty between intermediate algebra and college algebra, it isn't so much the content, it's the quantity of material that we cover in each section. In intermediate algebra, this would probably be the end of the section. I cover one concept and kind of beat it to death. In college algebra, we cover 2, sometimes 3, sometimes 4 concepts in a section, and that's what makes it harder. Again, it's not necessarily that the material is harder, it's just that there's just more material, more diversity in each section. So the next group of problems give me points. They don't give me a graph, but I copied the graph in here just because it will make my pictures prettier. You don't need graph paper ever for this class, so don't worry about that. When you're doing these problems, you can just draw blank graphs yourself. So the next group of problems are from 19 through 30, and they're another group of problems that don't have any algebra. They give me a point. So in problem 20, the point that's given is the point 24. And I'm asked to plot 3 different points. Part A is the kind of mirrored image over the x-axis. Part A says plot the point that's symmetric to it with respect to the x-axis. And to get that point, I want the x-axis to serve as a mirror. This point right here is considered symmetric to the original point about the x-axis because it's kind of the mirrored image over the x-axis. So this is for part A. This is the point that's symmetric with respect to the x-axis. If you're visual, you probably got that way before I did. I'm not that visual. And in order to get this, you just change the sign of the y. So these 2 points, relative to the x-axis is kind of the mirrored image. They're equidistant from each other with respect to the x-axis. The next one wants me to find the point of symmetry with respect to the y-axis. This is the y-axis. I'm just going to take this point and find its symmetry point. This point right here, they're both kind of 2 away from the y-axis. That's the point -2, +4. This is the answer to part B. That's the point that is symmetric to the original point with respect to the y-axis. And you get that by changing the sign of the x. So this is the point that is symmetric to the original point. And you do this by changing the sign of the x. Those 2 I can see all day, that these 2 points are kind of mirrored images about the y-axis. Those 2 points are mirrored images about the x-axis. It's not as clear to me the origin. To find the point that makes the origin, which is the point 0, 0, what's symmetric to, you have to change the sign of both the x and the y. So I'm going to change the 2 to a -2, the 4 to a -4. This point right here, the point -2, -4, if you look at the 2 points, the origin is kind of where their mirrored image is over each other. So I'd say this point right here is symmetric to the point 2, 4 with respect to the origin. And to do this, you change both signs. You change the sign of the x and the y. So each of the problems between 19 and 30, they give me a point, and I'm supposed to plot 3 additional points. The first point's going to be kind of the mirrored image over the x-axis. I do that by changing the sign of the y. The second point's going to be the mirrored image over the y-axis. I do that by changing the sign of the x. The third point is a mirrored image across the origin. You do that by changing both signs of the x and the y. So the next problem gives me the point -2, +5. To find the point of symmetry with respect to the x-axis, which is part A, I change the sign of the y. That's going to take me to the point -2, -5. And that's, I'm going to say this is the answer to A. These 2 points relative to each other are symmetric about the x-axis because they're equidistant, kind of mirrored images across the x-axis from each other. To do part B, to plot the point that's symmetric to the initial point with respect to the y-axis, I changed the sign of the x. This x was a -2. I changed it to +2. That's the point +2, 5. That's the answer to part B. This point relative to the original point, these 2 points relative to each other are symmetric across the y-axis. The y-axis kind of is the mirroring mark. And the last part, C, to find the point with respect to the origin, I changed both signs. So for the symmetric to the x-axis, I changed the sign of the y from 5 to -5. Symmetric to the y-axis, I change the sign of the x from -2 to +2. Symmetric to the origin, I change both signs. I change the -2 to +2, the +5 to -5. And that's going to be the answer to part C. So you can kind of see those points are symmetric about the x-axis. These points are symmetric about the y-axis. And those 2 points are symmetric about the origin, meaning the line that between the origin and that point would, if you did it, it would cut it into equal halves. Similarly, this line and that line would be equal halves if you put it across the axis that they're symmetric to. 24 starts off with the point +5, -1. First thing I want to do is find the point that's symmetric about the x-axis. To do that, so for the x-axis symmetry, you change the y sign. For the y-axis symmetry, you change the x, and for origin, you change both. So the initial point is the point 5, -1. If I change the sign of the x and plot the point 5, 1, those 2 points are symmetric about the x-axis, and that's what part A wants. If I change the sign of the y, or the x, to -5 and get the point -5, -1, these 2 points are symmetric about the y-axis. And if I change both signs, change the 5 to -5 and the -1 to +1, this point, -5, +1, relative to the original point, is symmetric about the origin. So these 2 points, if you connect those 2 points, the line would go through the origin, and they're kind of equal distance from the origin. Similarly, if you connect those 2 points, or those 2 points, the lines that connect the points, the axis would bisect those lines. 26 gives me the point -2, -7 to start. Relative to this point, if I change the sign of the y from negative, if I could actually plot that point, this is actually the point -2, -7. If I change the sign of the y from -7 to +7, gives me the point -2, +7. These 2 points are symmetric to the x-axis, and that's what part A wants. If I change the sign of the -2 to +2, that would give me the point +2, -7, and the initial point and this point that I just drew, those are symmetric respect to the y-axis. If I change both signs, the -2 to +2, the -7 to +7, this point and those points are symmetric about the origin. So this point right here was symmetric with respect to the x-axis. This point compared to the original point is, I can't spell symmetric. So it's symmetric with respect to the y-axis. I can't spell that either. And then this point right here is symmetric compared to the original point with respect to the origin, or the point 0, 0. So there isn't any algebra to do. This group of problems is leading into how to do the problems that require algebra. Like the beginning problems with the intercepts that I can do them without algebra kind of led into the problems that I did with algebra. These are supposed to do that same connection pretty soon here. Last 2 problems in this grouping, I'm given the point 4, 0. If I'm asked to find the point with respect to the origin, or to the x-axis, I'm supposed to change the sign of the y. Technically, for part A, I'm supposed to plot the point 4, -0, but the point -0 is hardly different than +0, because -0 is the opposite of 0, which is still 0. So this point, because it's on the x-axis, it is the point of symmetry to the x-axis. For part B, I change the sign of the x and get the point -4, 0. That's the point for part B that's symmetric to the y-axis, if you look at those 2 points relative to the y-axis kind of is the mirrored image of those 2 points. And for part C, I change the sign of both the x and the y. The x goes from +4 to -4. The y goes from 0 to -0. Technically, I'm supposed to plot the point -4, -0, changing both the signs, but -0 and 0 have the same. They're equal to each other, so I'm not going to write that as -0, -4, -0. I'm just going to write it as -4, 0. So once we get points that are on the axes, they're a little bit tricky. This point right here is both the point of symmetry to the y-axis and the origin. So if you look at these points relative to the origin or relative to the y-axis, they're kind of mirrored images of each other about those. Last one, 0, -3 plots on the y-axis. To do part A, I change the sign of the y. I get the point 0, 3. This is the answer to part A. This is the point that's symmetric to the x-axis. To do symmetric to the y-axis, technically I get the point -0, -3, but the point -0, -3 is the same as the point 0, -3 should I say. So this is also the answer to part B. This point, because it's on the y-axis, is the point of symmetry to the y-axis. And the last one, I'm going to go -0, change the sign of the x, and change the sign of the y to the point -0, 3. -0 is the same as 0, so that's really the point 0, 3. So that point 0, 3 is the point of symmetry to both the x-axis and the origin, and the point itself is the point of symmetry with respect to the y-axis. Okay, those are the kind of warm-up, and there's even a little bit more warm-up before we get to the algebra. The next group of problems give me pictures, and sometimes I don't have enough problems, and that's the case here. I didn't know if I had enough problems to properly do them, so I'm just doing some of the odd problems for you. So I'm probably going to do all the problems between 31 and 38, and it's, in some sense, I think, easy. So I'm supposed to, from a picture, figure out what kind of symmetry it has. A graph has symmetry to the x-axis if I can draw a line through the x-axis and it makes equal pieces. So for this graph right here, that looks, something like this. If the x-axis itself divided the graph into 2 identical pieces, I would say the graph is symmetric to the x-axis. It's definitely not symmetric to the x-axis because the line through the x-axis, the top and the bottom halves don't look the same. If I draw a line through the y-axis, and it makes equal halves on either side, we say it's symmetric to the y-axis. This line through the y-axis, that looks like the left and the right halves are perfectly the same. So I'd say this is symmetric to the y-axis. Definitely. For symmetry to the origin, it's not 100% check, but it works 95% of the time, and it'll work every time, I think, for us. For symmetry to the origin, it has to be the case that any point on it would have to have a point with both its x and y signs changed. That's not so easy to find. So the way I usually check for symmetry to the origin is I turn it upside down. If it looks the same upside down as right side up, I think it has symmetry to the origin. Probably not spelled right. That's the way I check for origin symmetry. Again, there are some graphs that look the same right side up as upside down that don't have origin symmetry, but I don't think that comes up in this class. It's just not that big of a deal. For the longest time I didn't teach symmetry. It's not like the biggest deal, but some teachers in Math 182 need you to know a little bit about symmetry, but not origin symmetry, but they make me teach it anyways. X and Y axis symmetry a bit. So if I look at this graph and I flip the page over, had it looked exactly the same upside down is right side up, then it would have that symmetry. But upside down, it looks like this, and that's not exactly the same as that. It's flipped over of that, and that's not exactly the same, so it doesn't have origin symmetry. This only has symmetry to the y-axis. It's the origin symmetry that's going to be a little tricky, but the x and the y-axis won't be that tricky. 32, so I'm done with this. The only symmetry that 31 has is that to the y-axis. Similarly, 32, the only symmetry it has is to the y-axis. If I draw a line through the y-axis, it makes perfect equal halves on either side of the y-axis. That's what it takes to have that symmetry. A line through the x-axis doesn't do anything because it doesn't cut the graph into equal. It doesn't cut the graph at all. And if I flip it over, it's not going to look the same. This is only symmetric to the y-axis. (33) and 34, hopefully those are moderately obvious. If I draw a graph, a line through the y-axis, it doesn't cut the graph at all, so it's not symmetric to the y-axis. If I flip it over, instead of pointing to the right, it's pointing to the left, so it doesn't have symmetry to the origin because it doesn't look the same upside down as it does right side up because it's going a different direction. But it does have symmetry to the x-axis because if I draw a line through the x-axis, it cuts it into equal halves. So this one has, the only symmetry it has is it's symmetric to the x-axis. Similarly, 34, if I draw a line through the y-axis, it doesn't cut it into equal halves. The half to the left of the y-axis doesn't look like the half to the right of the y-axis. If I draw a line through the x-axis, the half above the x-axis and the half below the x-axis look exactly the same, so it's symmetric to the x-axis. And if I flip the page over, instead of opening to the right, it's opening to the left, which isn't the same, so it's not symmetric to the origin. So both 33 and 34, the only symmetry they have is to the x-axis, because the x-axis is the only line that cuts them perfectly in half. The next two problems, if I look at the x-axis, this isn't a line of symmetry, because for the x-axis to be a line of symmetry, this piece up here would have to be down there, because to have x-axis symmetry, the line through the x-axis, anything above and below the x-axis have to look identically the same. And for this part of the graph, there's no counterpart above the x-axis. For this part of the graph, there's no counterpart below the x-axis. So it's not symmetric to the x-axis. Similarly, it's not symmetric to the y-axis, because to be symmetric to the y-axis, this part up here would have to have a mirrored image over there, and this part down there would have to have a mirrored image over there. So it's not symmetric to the y-axis. But when I turn this graph over, well, let me draw it on a separate sheet of paper. So the graph looks something like this. And when I turn it over, if I compare what I just drew to what I initially had drawn, not that you can see it, but if I compare what I just drew to what initially, so this is a copy of that graph. And now I'm going to flip it over. And when I flip it over, because it looks the same as the original graph, that's what it means for me to have symmetry to the origin. There are probably better ways to visualize that. I'm just not that visual, so that's the best I can do with symmetry to the origin. If it looks the same upside down and right side up, I'd say it has it. There are times where that test fails you. It looks the same upside down and right side up, and it doesn't have that symmetry, but I won't give those to you. Same thing with problem 36. It doesn't have symmetry to the y-axis because this part doesn't have a mirrored image across the y-axis. Doesn't have symmetry to the x-axis because this part doesn't have a mirrored image under the x-axis. But it is going to have symmetry to the origin. And again, if I just copied this graph the best I can, graph looks something like that. If I take this graph and if I flip it over, turn it upside down, When I turn it upside down, if I look at, so this is a graph not flipped over. I flip over the graph. If it looks the same flipped over as it does to start, then we say it has symmetry to the origin. Two more graphs. For 37, this is not symmetric to the y-axis, because to be symmetric to the y-axis, there would have to be equal halves inside of the y-axis, and these two halves don't look like each other. It's not symmetric to the x-axis, because there need to be something above the x-axis that looks like that. And if I flip this thing over, so the initial graph looks like, more or less like this. If I flip it over, it has to look identical to how it started, and it doesn't look identical to how it started. So it's not symmetric to the x-axis, it's not symmetric to the y-axis, it's not symmetric to the origin. This has no symmetry, at least with respect to the x-axis, y-axis, and the origin. 38, not symmetric to the x-axis because the y-axis, because the part of the graph to the left of the y-axis doesn't look like just like the part to the right of the y-axis. Not symmetric to the origin because the x-axis, because the part above the x-axis doesn't look like the part under the x-axis. And then for origin symmetry, it's not going to look exactly the same flipped over. So if I take this and I flip it over, this is the graph to start, this is the graph flipped over. Those don't look exactly the same, so it doesn't have symmetry to the origin, so it has no symmetry. That's the last of the non-algebra stuff. Now we get to the algebra stuff. And for the algebra stuff, I'm going to resort to my calculator to save me a little bit of work. So my calculator is going to give me an idea of what the answer is, but I have to confirm the answer by hand. So I'm supposed to determine from this equation in number 40, which is, if you can't read it, y squared equals x plus 1, whether it has symmetry to the x-axis, the y-axis, or the origin. I'm going to sketch a graph to determine what I think the symmetry is, and then I'm going to verify my answer with algebra. So first thing to do is sketch a graph. You don't need graph paper. You really probably need a calculator though. To sketch a graph of this, just like when I sketched a graph earlier that I had to do square roots, I have to do square roots here. My calculator can't graph a y squared. So I'm going to go square root plus or minus square root. On the left side, I'm going to cancel out the squares and get a y. And on the right side, I get plus or minus the square root of x plus 1. On my calculator, I'm going to enter y1 equal the square root of x plus 1 and y2 equal the negative square root of x plus 1. I'm going to graph those. I'm going to look at the graph and figure out what kind of symmetry, if any, I think it has. And then, after I think I know the symmetry, I'm going to do the test. And the tests aren't terribly hard, but I haven't done anything yet. So on my calculator, clear out the stuff that's in there, hit my y equals button, clear on the lines that needed to be cleared. First one, I go second square root of x plus 1, close out the parentheses, equals, and then use the negative sign in the bottom row of my calculator, and then second square root x plus 1, enter. Those are the two functions I needed to enter. I have a nice window in there already, so I'm just going to hit my graph button. I'm going to stare at this graph the best I can. It's half parabola on its side. Kind of doesn't matter if I do a perfect representation of that, but I need something that's reasonable. So the graph looks, something like that, and better on my calculator than it does by hand. To me, I suspect the only symmetry it has is to the x-axis. So I believe the answer to this problem, what kind of symmetry does this equation have? My answer is I believe it's symmetric only with respect to the x-axis. I'll say to the x-axis. If this is a test question, you did this and did no more, then you'd lose probably most, if not all, the points. I need to confirm my guess via algebra. And to confirm a guess, so this is what's required. To confirm the graph is symmetric to the x-axis. And the confirmation comes from the group of problems that we did with the points. When I was asked to create points, and I created points that were symmetric to the x-axis, what I did with it, I had a point and I wanted to find the point of symmetry to the x-axis, I changed the y. Somewhere's up here I did that. So when I was asked to find the point of symmetry with respect to the x-axis, I changed the y. That's what the algebra test is going to have me do. So what's required, the algebra that's required to show that this is not an optical illusion, this is really symmetric to the x-axis, is I need to replace the x, I'm supposed to change the y, because when I'm doing symmetry to the x-axis, I change the y. And what did I change the y to? I changed the sign of the y. So I'm going to replace the y with a negative y and simplify. If my problem simplifies to the original problem, I will have confirmed my answer is correct, or have shown my guess is correct. So graphing isn't enough. It doesn't actually verify 100% that you have that symmetry. To algebraically prove that an equation which has a graph has the symmetry that you suspect it has, you have to do a physical test. The test to show a graph or an equation is symmetric with respect to the x-axis. I'm going to replace the y with a negative y, and I'm going to simplify. If when I simplify, I can get something that's exactly the same as the original problem, then it has that symmetry. If when I simplify, it doesn't simplify to exactly the original problem, then it doesn't have that symmetry. So I'm going to go to a different sheet of paper, and this is what would be, this is required. So this is the actual work that is needed for problem 40. The original problem was y squared equals x plus 1. What I'm required to do is I'm required to change the y to negative y and simplify. So I'm going to go negative y quantity squared equals x plus 1. And it's almost no algebra. If I get rid of the exponent, I get negative y times negative y equals x plus 1. I'm multiplying two negatives, so the left side simplifies to be a positive. And I'm multiplying two y's, so I get a y squared. So when I change the y to negative y, write it without the exponent, write it with repeated multiplication, the left side simplifies to be the original problem. So because this reduces exactly equals the original problem, I know for sure the answer, it's symmetric to the x-axis, is correct. So my answer, if this was a test question, the answer I would just say it's symmetric to the x-axis. You don't need to show me that you graphed it on your calculator to know which algebra to do, but this is what you need to show. So if this was a test question, if you showed this and that for an answer, that's all you need to show. Next problem. 42 gives me the equation x squared plus y equals to 2. Same deal. I'd like to graph these things so I have an idea of what the symmetry is. So I'm going to graph, but my calculator doesn't know how to graph x squared plus y equal to 2. My calculator can only graph when an equation is solved for y. So I'm going to solve it for y. I could write 2 minus x squared, or I can write negative x squared plus 2. It doesn't really matter. Both of these I can enter on my calculator, but I have to use different negatives. So I'm going to enter this on my calculator. I'm going to graph it. And that graph should let me have an idea of what the symmetry is. So I'm going to graph 2 minus x squared. You could do negative x squared plus 2. This is going to take the minus that's above the plus sign. This version would take the minus in the parentheses. So it's gonna, you have to get used to the right negatives. So y equals clear, clear, and then 2 minus x squared. The x is there, the squared is there, the minus I used was that. If I cleared this and did negative x squared plus 2 using the negative in the bottom row of the calculator, these graphs will be identical. 2 minus x squared and negative x squared plus 2 are equal to each other. When I hit graph, I get that picture. I'll try to duplicate that. I don't have to duplicate it that accurately. So this picture looks something like that. When I look at that, it doesn't look to be symmetric to the x-axis. It doesn't look to be symmetric to the origin. The x-axis doesn't produce equal images above and below the x-axis. Flipping it over, I don't get the same thing. It appears to be to have y-axis symmetry. And if this was a test question and you didn't show any algebra, then I couldn't give you points. So the algebraic check to see if something has y-axis symmetry is I need to change the x to negative x and see if it reduces to the original problem. If when I change x to negative x, if it reduces to the original problem, then it has that symmetry. So it's a test for y-axis symmetry. I replace the x with a negative x and simplify. If it turns into the original problem, then it has y-axis symmetry. If it doesn't reduce to the original problem, then it doesn't have y-axis symmetry. So I'm going to go off to another piece of paper here because I don't have so much room here. So the original problem 42 is x squared plus y equal to 2. I'm going to test only for y-axis symmetry, because I don't think it has the other symmetry, and I don't want to do 3 tests for every problem. It would take forever. So my graph gives me the idea of which test I need to do. There's 3 different tests. Testing for x-axis symmetry, you change the y to negative y. Check for y-axis symmetry, I'm going to replace the x with negative x. So doing this, you'd get negative x squared plus y equals to 2. Negative x squared is negative x times negative x. When you multiply 2 negatives, you get a positive. When you multiply 2 x's, you get an x squared. Because the original problem and what I get when I simplify by changing the x to negative x are identical, then it has symmetry to the y-axis. So my answer for this is the graph has y-axis symmetry. If you just wrote symmetric to the y-axis or y-axis symmetry, that would be all I need to see. All right. Keep trudging along on this. 44 is the first one I can graph without doing any rewrites because it's solved for y. So I'm going to sketch a graph real quick. Y equals clear 3x up arrow using the exponent because the cube isn't, there's not a special key for the cube. So the little caret button and then 3. See these things. So 3x cubed, and I hit a graph. It looks like that. So the graph again looks something like that. That definitely doesn't have y-axis symmetry nor x-axis symmetry because it doesn't have reflections above the x and the y-axis. But if I turn this thing over, and if I look at the graph straight up and upside down, it looks like it has symmetry to the origin. So I guess this graph is symmetric to the origin. It's not enough to guess. I have to do the algebraic test. When I was working with the points to get the origin symmetry, I had to change both the x and the y. That's what I'm going to have to do here. So to test for what I think is the right answer, to test for symmetry to the origin, I change the y to a negative y and x to a negative x, and it has to reduce back to the original problem. This is the hardest one for checking. So here I'm going to go negative y equals 3 times negative x cubed. Notice I didn't put the y in a parentheses. I could have, but I didn't. And now I'm going to go and get rid of the exponent. Negative x cubed is negative x times negative x times negative x. When I multiply 3 negatives on the right-hand side, I get another negative. So this negative, and that negative multiply to be really a negative 1. Because if I want to really emphasize, this is 3 times negative 1x times negative 1x times negative 1x, because that's what the negative x's mean. And so this is really 3 times negative 1 times negative 1 times negative 1 times x times x times x if I want to separate the negative 1's from the x's. These numbers right here multiply to be negative 3. So I get negative y equals to negative 3, and those multiply to be x cubed. That's not the original problem. So I separated negative x cubed into the negative x's, which were negative 1x's, multiply the negative 1's together, multiply the x's together, and now I'm going to multiply both sides by a negative 1. On the left side, negative 1 times negative y, I multiply 2 negatives, I get a positive. On the right-hand side, negative 1 times negative 3, I get a positive 3. Because the original problem, 3x cubed, and what I get when I do a bunch of simplifying are exactly the same, then my answer is the graph has symmetry to the origin, and I've shown it algebraically. So my answer, I'm just going to say symmetric to the origin, symmetry to the origin, and this is the test that you have to do. It's the hardest of the tests. The x-axis and the y-axis symmetry, usually only get x-axis symmetry when you have a y squared. You usually only get y-axis symmetry when you have an x squared. And those tests are real easy because when you square a negative, it turns into a positive. To have origin symmetry, you usually have to have odd exponents. You can have even exponents, but it's usually with odd exponents, and the odd exponent test is a lot harder. For 46, I can't read it here, so let me write it bigger just in case you can't see that. 46, you get y equals to x squared minus 3x minus 4. I can graph that just how it sits. So y equals clear x squared minus 3x minus 4. Graphed lovely parabola. Oh, can't tell exactly how it looks. Something like this. Again, I'm not looking for super accuracy here. That's a reasonable representation of what my calculator gave me. Doesn't have symmetry to the x-axis because the x-axis is not mirrored image above and below the x-axis. It doesn't have symmetry to the y-axis because there's not equal pictures below and below the y-axis. And if I turn the graph over, it doesn't look exactly the same turned over as it does right side up. So I don't think it has origin symmetry either. So my guess is this has none of the symmetries. And because it doesn't have any of the symmetries, I'm not going to do the algebra because all the algebra is going to fail. I wouldn't be able to reduce the modified problem with the negatives back to the original problem. So I'm not going to do any algebra when it doesn't have symmetry. (48). Getting to the end here, and sometimes I start speeding up at the end. I'm sorry about that. These things, they have to be way harder as a student than it is as a teacher. But these things really, they tend to wear me out. So by the time you watch the video, I imagine you don't want to do any more math, and that's completely understandable. So I'm going to graph this. It's solved for y already, so I don't need to do anything but graph it. So I get y equals x squared plus 6. Graph. Looks to me like it has, well, you can barely see the graph. It's way up here on my calculator. But it certainly looks like it has y-axis symmetry. My guess is it has y-axis symmetry, so I'm going to test only for y-axis symmetry. And the test for y-axis symmetry is I change the x to negative x. So I'm going to go negative x squared plus 6 equals to y. Negative x squared is negative x times negative x. On the left-hand side, the two negatives multiply to be a positive. Two x's multiply out to be x squared. Because I was able to change the x to negative x and it simplified exactly to the original problem, then my guess is going to be correct. And the answer that I'd write if this was a test question, I'd say it has y-axis symmetry, or I could say it's symmetric to the y-axis. Those are just different ways of saying the same thing. Got to be getting close to the end of this. 50 gives me the equation y squared minus 3 equals to x. I need to get it solved for y. I'm going to add 3 to both sides. Give me y squared equals x plus 3, and then square root plus or minus square root. I get y equals plus or minus the square root of x plus 3. So on my calculator, I'm going to go y1 is the square root of x plus 3. y2 is the negative square root of x plus 3. See where that takes me. So y equals clear, first one, second square root of x plus 3, close out the parentheses, and then negative in the bottom row of the calculator, second x squared for the square root, x plus 3, graph it. It's a parabola on its side, looks something like this. So it looks like it has symmetry only to the x-axis, so I'm going to test only for symmetry to the x-axis. To do that, I change the x to negative, I change the y to negative y, and I simplify. So I'm going to go, does negative y squared minus 3 equal to x, which is the original problem, with the y changed to negative y, simplify to the original problem? Well, negative y squared is negative y times negative y. Two negatives multiply to be a positive. Two y's multiply to be y squared. Because the original problem is what I get when I change y to negative y and simplify. The answer is this has x-axis symmetry. You don't have to show any graphs, but I would probably graph everything on my calculator just for safety. You have to show the test. The test for x-axis symmetry is changing the y to negative y and simplifying. That's usually easy because just the squares usually just go away. Usually you have x-axis symmetry when you have a y squared. You have y-axis symmetry when you have only an x squared. And then origin symmetry can be tricky, but usually you have odd exponents. Oh, that's the whole thing. Oh, thank gosh. So tempted to do another problem, but I'm kind of tired of doing these. Take a stab at the homework and see where it takes you. The symmetry stuff at the end might be, a bit tricky, and if it's completely okay if it is, you come and visit me in my office or send me an email and I'll try to do my best explaining it. There's usually a symmetry problem like this on every test. So make sure you get good at them before we do the test. All right, so that's got to be enough. Hopefully between now and before you watch the section 2.2 video, you do all the odd problems from section 2.1, and any odd problems that you can't do, let me know and I'll try to help you out.